Tower, this is JetBlue Flight 271, requesting approach pattern for final. JetBlue Flight 271, this is we copy, working on that information now.
An approach path for an aircraft landing is shown in the figure and satisfies the following conditions. The cruising altitude is h when descent starts at a horizontal distance L from touchdown at the origin. 2. The pilot must maintain a constant horizontal speed v throughout descent. 3. The absolute value of the vertical acceleration should not exceed a constant k, which is much less than the acceleration due to gravity. First, we must find a cubic polynomial p of x is equal to ax cubed plus bx squared plus cx plus d that satisfies condition 1 by imposing suitable conditions on p of x and p prime of x at the start of descent and at touchdown. Use conditions 2 and 3 to show that 6hv squared over L squared is less than or equal to k. Suppose that the airline decides not to allow the vertical acceleration of the plane to exceed k is equal to 860 miles per hour squared. If the cruising altitude of a plane is 35,000 feet and the speed is 300 miles per hour, how far away from the airport should the pilot start descent? So for the first part of the question, we're trying to find the cubic polynomial that fits our graph. So we want to get it in term p of x is equal to ax cubed plus bx squared plus cx plus d, cubic polynomial that fits our graph. So before we do that, there are a few conditions that we should of our own that we want to put, such as p of 0 is equal to 0, because the distance at the origin is the height. The distance of 0 gives you a height of 0 because the plane has already landed, shown by the graph. So at 0 the height is 0, so position 0 the height is 0. P prime of 0 is equal to 0 because at the origin the plane is on a horizontal tangent, so the slope would be 0. P prime of L is equal to 0 because at distance L the plane has just started descent, so it would be on a horizontal tangent because it was at cruising altitude. So at P prime of L is equal to 0 because the slope of the tangent is 0. And lastly, P of L is equal to h because at distance L the height is h at the start of descent. So knowing this, we can start to work on getting our cubic polynomial. So if we plug 0 into our polynomial, we would get that we get d. So in order for p of 0 to be 0, d needs to equal 0. So d is equal to 0, so we don't have to worry about that anymore. And so now if we derive this function, we get, and from our second condition we know that p prime of 0 is equal to 0. So we plug in 0 for our derivative, for a derived function, we get c. So here we know that c is equal to 0. So we don't have to worry about that anymore. So what we get here is that our function is p of x is equal to ax cubed plus bx squared. So now knowing this, we can use our third condition, p of L is equal to 0. P prime of L is equal to 0. So we get our derivative and make it equal to, substitute x for L and make it equal to 0. And since we're trying to find our function in terms of h and L, we're going to try to substitute a, so we get a alone. So a would equal negative 2b over 3L. We can substitute this back into our original equation. P of x is equal to negative 2b over 3L x cubed plus bx squared. Now we're trying to find b in terms of h and L. So our last condition, p of L is equal to h. We can substitute L back into our equation and make the whole have the function equal to h. One third BL squared is equal to h. Because remember, P of L is equal to h. So this right here is going to equal h. So if we get it B alone, we get B is equal to 3h over L squared. Now that we have B, we can substitute B back into our what we got for A to get in terms of h and negative 2h over L cubed. So now we have A and B. We can then get our cubic polynomial for our function, which would be y is equal to p of x, which is equal to negative 2h over L cubed x cubed plus 3h over L squared x squared. And here is our cubic polynomial. So for our second question, use conditions 2 and 3 to show that 6hv squared over L squared is less than or equal to k. So pilot must maintain a constant horizontal speed throughout descent. Alright, the absolute value of the vertical acceleration should not exceed a constant k, which means from our function, since we know we derive this twice, we will get our acceleration. So the absolute value of our acceleration should be less than or equal to k. Alright, so before we start, we should note that dx dt is equal to a negative v, because the pilot is descending, so velocity is negative. Alright, so if we start with our function. Multiply it out, we get p prime of x is equal to, it's going to be a positive 6 because remember dx dt is equal to a negative v, so it's going to be 6 h v x squared over L cubed minus 6 h vx over L squared. Alright, so this is our velocity function. So if we derive this one more time, we will get our acceleration function. So alright, so for this next part we need to look back at the graph and note that when time is 0, remember time from start of descent to landing, the start time is 0. So when start time is 0, the distance is L. So when t is equal to 0, x is equal to L. So we can use this and substitute L for x in our equation. P double prime of L is equal to negative 6 hv squared over L squared. Alright, so this is what we got for acceleration. But what it tells us, one of our conditions is that the absolute value of the vertical acceleration should not exceed constant k. So the absolute value, so we get the absolute value of this is going to be less than or equal to k. So 6hv squared over L squared is less than or equal to k. So here's our last question. Airline decides not to allow vertical acceleration to exceed 860 miles per hour squared. So k is equal to 860 miles per hour squared. The cruising altitude of the plane is 35,000 feet and the speed is 300 miles per hour. How far away from the airport should the pilot start descent? So from what we got from our last problem, 6hv squared over L squared is less than or equal to k. Here is L is a length at the start of descent. So we can find L, we can find out how far away the plane should start descent. So all we need to do is plug in what we got. So k is equal to 860 miles per hour squared. height is equal to 35,000 feet, because that is the cruising altitude. And the speed, so our velocity is equal to 300 miles per hour. So now we can plug these back into our equation. So the pilot should start descent at roughly about 64.5 miles out.
JetBlue Flight 271, this is Tyler. Destination about your descent, 64.5 miles out for final. I'll copy. Copy that, Tyler. JetBlue Flight 271, coming in on final.
100. 50, 40, 30, 20, retard, 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 retard.
I love making the last clap.
Me too.
Ladies and gentlemen, JetBlue Airways would like to welcome you to Cancun, Mexico. Local time is 10:50 a.m. Please keep your seatbelts fastened and carrying items stowed until the seatbelt sign is turned off. Be careful when... Did I say p.m.? In case I did, I said a.m. Please remain seated until the captain turns off the fasten seatbelt sign. Be careful when opening overhead bins as it tends to move during flight. If this is your final destination on JetBlue, your checked baggage may be claimed in the carousel on the lower level. If you have a bag tag receipt that says claim at gate, you may claim those items at the front aircraft door or on the carousel on the lower level. For those customers needing special assistance in planing the aircraft, please remain comfortably seated once we arrive at the gate so we may better assist you. At this time, you are welcome to use your cell phones only if it's readily accessible. The next time you're online, please visit JetBlue.com for newest routes, as possible fares, and information on TrueBlue, our customer loyalty program. On behalf of all of us here at JetBlue Airways, thank you very much for joining us today. We hope to see you again soon. Have a great time.
That's like off. Check.
You're right.
Here, left side. Check. Low for study speed.